now I pushed it all the way to the right side. Thank you. So A and B. So smallest positive number, right? Satisfying this condition. So it should be positive. For smallest positive number satisfying this condition is called the least common multiple, and we use this expression LCM. And by definition, we have this kind of technical part. So instead of saying this thing, people usually say this thing. If there is another number satisfying this, right? If there is another number satisfying this, then L is smaller than C. Do you follow me? So this, instead of describing it using this sentence or word or phrase, people say if there is another number that is divided by both A and B, then the number should be greater than or equal to L, because L is the least. So it's the technical part defining the same thing. So this is the rigorous definition, and this is the rough definition, just by using sentences. And if you don't have a question, then I will continue. Then the next thing is proving the theorem. And the theorem says this. For any positive number AB, GCD of AB and LCM of AB multiplied together gives us A times B. So this is the fact. First of all, instead of proving it, we will use some example. So you may pick two numbers so that we can examine this fact. Instead of proving it, we want to examine the fact. So please give me two numbers. 4 and 7. Then what is the GCD? GCD of 4 and 7 is what? 1. LCM, least common multiple of 4 and 7 is 28. So GCD multiplied LCM is 1 multiplied 28. 4 multiplied by 7 is 28. So and let's use a little bit different numbers. GCD of 12 and then GCD of 16, right? 12 and 16. Then LCM of 12 and 16. First of all, GCD, greatest common divisor. The biggest number dividing both numbers is 4. And the number that is divided by both numbers is 48. Do you follow me? If you can find any smaller number divided by both numbers, let me know. So while you are examining and browsing, I will pause, and then once you get the idea, I will begin to prove it. The key is the proof. Any questions? Then let's do it. So for convenience, as we did before, let's call G the GCD. So I will, GCD of AB, right? GCD of AB is called G, and then L is LCM of AB. So just the definition, right? Define. Then we can write A using the divisor. A is divided by G because it's the common divisor, right? Or divisor. So G is the divisor of A. So A equals G times some number, say X. And all the numbers that we handle here are integers. Any questions? A equals g times x. And then b equals g times y. Then least common multiple, L equals g times x times y. Why? Because g times x is a. So L is divided by a, g times x, right? And then L is divided by g times y, g times y is p. So L is divided by both a and b. So the only thing remaining is showing that this g times x times y is the smallest. Then we are done in this proof, right? So I say claim because I claimed it without proving it. So I claim that the least common multiple is g times x times y. Do you follow me or not? You should know the reason. It is obvious, right? Why do we need a proof? But we need a proof. But in any case, you should understand the flow, right? So G is the divisor. G is the divisor, so A is G times something, B is G times something. And then least common multiple should be G times X times Y. This is the claim. Then, as you can see, at least even though it's not the least one, we can say it's a common multiple, right? We can at least say, so I said this, so let's say L1. Right? But because this claim is okay, so let's call this part capital L, right? For convenience, right? So capital L is defined this way: G times X times Y is capital L, and my claim is capital L is nothing but the LCM, least common multiple. So let's show that L is the smallest possible number in this direction. So to use GCD, we will use this fact. G equals, what can you say? Because it's GCD of A and B, we, instead of using GCD letters, we can represent G using mathematical expression. What is it? So because we used X, let's say A times capital A, and then B times capital B. Instead of using XY, I will say this. G is the greatest common divisor. Then, let's finish it. Because of this reason, we can write it this way. L equals sorry, I call this capital L. The claim set is L, so I will use my definition. Capital L equals this thing. So it equals just a moment. I think I already overloaded, so this overloading is not necessary. Sorry for that. I will divide by. So let's do it this way. Right, so I overloaded it. So let's stop this direction because it's already overloaded. AB is divided by G. And take a look. I'm a little bit confused. I should show capital L is the smallest possible one. So I will intentionally make another one to show, because this is already explained upstairs. L is nothing but this gx gy divided by g. That is the claim, right? So this is just definition. It doesn't go anywhere. I will show this thing by using, assume that C is equal to, C is the common multiple. C is a common multiple.
Why is that equal to gxy?
It is defined right here. A equals gx. B equals gy. I defined.
But when you have like g times x and g times y, all over g
G times x, g times y, a is g divided by g. Right, yeah, so yeah.
I got it.
This is the definition of L. So the missing part is not this part. Common multiple, any common multiple will be greater than this L. That is the goal, right? So assume that C is a common multiple of A and B. Then C is equal to A times some number, because we use the capital X, I will use P, and then C is B times P, Q. Because I already used XY, we will use P and Q. So it's a little bit long, but now we're using this idea. I will show that C is greater than or equal to L. So the key part here is the proof of this thing. This L is the smallest possible one, and then meaning it becomes LCM. Then we are done. So this part is the one that I want to show you. And to show that, I will use technical thing, right? Assume that C is the common multiple of the two. Then you use this, I will create bigger GCD, or the same GCD, right? So I will pause and then go to the next page. So let's cook. We have all the necessary ingredients, so it's time to cook. So C equals A times P, and then C equals B times Q, and then, as you can see, GCD of AP, BQ, right? GCD of AP, BQ should be greater than or equal to GCD of just a moment, GCD of what I'm complete, yeah, P and Q. P and Q, A, B. GCD of P and Q is greater than or equal to 1. In other words, C is a common multiple of A and B, so C equals A times some number, and then B times some number. Then we track down those part, P and Q, instead of A and B. So if we get something bigger here, then we got the bigger number C. Do you know what I mean? Right, we got the bigger number C. So with these things, I can write C. So let's write this GCD, and because there are so many letters, I will use K. So K is greater than or equal to 1, and then K GCD is some number P times M, and then Q times N. So we are getting the GCD of P and Q, which are these numbers. So let's combine everything together to make this thing. So if we multiply both sides by AB, then AB multiplied together gives us I'm completely confused, because if I multiply AB here, will it be bigger? AB P and Q should be greater. Okay. I'm completely confused. If we multiply P and Q, K is this one. I should leave just a moment, please. I'm considering about GCD, AB divided by LC. Should be greater. So I will, instead of overloading it, I will underload it. P equals C over A, M. Q equals C over EN. Then PQM AB. CB, I'm completely lost here because of many calculations. Do you find the point that I can recover? See, K is greater than or equal to 1. So this should be the direction. And then PQ, and then this thing. From this, how can I get out? If I multiply G everywhere, Just a moment. If I multiply G everywhere, I should have divided. I'm completely confused now, so I'm very sorry because roughly my idea is dividing. I multiply by it should have been the division. So I'm completely confused here, and it's not a good idea to go any further and make things worse. Because if I divide this by G, then G will divide this, G will divide this, and then I should show that this is 1. Then C is greater than or equal to L. This is the direction. But I'm currently completely confused.
Is this theorem 2.8?
Yes, right, 2.8. So I should divide this by G, but something is bothering me very much because I couldn't show the part. So I should divide both sides by G. Then AB divide by G is by definition L, and then G divides this thing too. Then B divided by G is called XM, and then YM, right? YM, and then XN, and then less than or equal to L. The part that I was bothered was the fact that this is 1, because I do not know whether this direction will lead to 1, because if it leads to 1, then C is greater than and the proof is finished, but I cannot track down all the things that I wrote down. So I'm very sorry. I will return back to this next time. But roughly, as you can see, even the simple thing can be very confusing when you want to really prove. So I am stuck here. I do not know how to create 1 from this thing. Sorry for the mistake, and let's continue. Because if you have enough time, I may spend like 30 minutes and so on, but it's not a good idea to go any further because of the definitions and the confusion. In any case, the next case is the corollary to this one. If LCM AB is nothing but A times B if GCD is 1 because of this fact. Because if we multiply GCD and LCM, it is AB, but if it's 1, then automatically A times B by is corollary to the previous one. The next one is really calculating the LCM, and because of this reason, LCM calculation is nothing but AB over GCD calculation. Do you follow me? So essentially, we don't even have to spend much time on LCM because once we find GCD, then AB multiplied by GCD is the result. So in fact, I do not even cover LCM part because of this fact. The only thing that I missed was the proof of this thing, right? The only thing that I missed was the proof of LCM GCD equals, right? LCM multiplied GCD equals AB. This is the missing part. But once this is done, then take a look. If you need LCM, just divide by GCD because you know about GCD. Do you follow me? So this is it. Then what else? Roughly this is it. So the only thing missing is proving that any common multiple is greater than L, and then to show that I should show that this is 1. But I didn't. Yes?
GCD of X and Y is equal to 1. So
Right. Right. So that's that kind of thing. But I couldn't track down what I wrote down on the previous. If I go to the previous page, I lose this page on this software. So I scattered everything there. That's the reason why I was stuck. And then I will make a nice version next time and then show you. Instead of, because as you mentioned, x, y are relatively prime. And then we can get this equal to 1. But not in this form. It's a little bit unorganized. So let's return back to this problem later. In any case, LCM is nothing but, sorry. LCM is nothing but AB divided by GCD, right? This is it. In other words, you know GCD, you know everything. But what we need to know is this fact, right? G times L equals A times B, right? And we need a proof of this thing. And I was almost there, but couldn't quite nail it because I had all the definitions scattered around, and I couldn't quite link those things to lead to one. So key part that I couldn't do it now is this thing, and then next time I will reorganize the letters and then show that this is 1. Then C times 1 equals greater than equal to L, meaning C is, L is the least, right? Least. In any case, this is the direction to prove, but even the small proof can be quite complicated, right? If you go the wrong direction or if you are not organized. But as you can see, it's very difficult to study proofs because most people found proof after trial and error. To prove one thing, people do not just think of the proof straightforward. No. They try this way, that way, and then go this direction, that direction, and then make mistakes. And then later somehow arrive at the result. Then people try harder to find shorter way or a cleaner way, and then they write down the neat, clear, easiest version or best version. Without memorizing the best version, you cannot really drive it. So you saw how people really drive, because I didn't memorize the proof at all. I tried to use principles and then try to come to this conclusion. C is greater than or equal to L. But what I couldn't link was this thing. So to link this thing, I should make those definitions very tight in the first place. Then I can come to this clean way. But I lost the track, so I decided not to spend more time on this thing. But next time I will create a link and then show that this is 1. That means L is the smallest. That means this is, so once we show this, then this means this L is the least common multiple. In any case, you saw that this kind of thing requires some kind of organization. If you don't have a question, we will continue the prime number direction. Questions? Last time I proved that there are infinitely many primes, and the fact itself is important, but more important thing is right? There are infinitely many prime numbers, and the more important thing is the way Euclid proved the fact. How? You assume that there are only these many primes. So all the primes in the world is collected. Then these are all the possible primes. There are no more primes than these things. Then what he did was then multiply all these primes in the world, right? These are all the primes, and then add 1. Then call this number, I didn't know what letter I used, maybe N, it doesn't matter. Then, because of the strong assumption, these are the only possible primes, we also claim that this is the prime, because some number is divided by some prime number, right? Any number is divided by some prime number, right? Any number is divided by some prime number. All the prime numbers are checked to divide, but n is not divided by p1, p2, or pn. N is not divided by these numbers. That means n is also prime, right? Because if it is not divided by any prime number in the world, then n should be prime. That means a contradiction, because in the first place we assume that these are the only possible primes, but now we have one more prime. Then contradiction. But people sometimes misunderstand this proof. People think, oh, if these are prime numbers, then this is a prime number. No, it's not the fact, because assume that we have only these primes, then this is prime. But we have many primes than these things. In other words, between this number and the number, there is a huge gap. And there are very many numbers. There are very many numbers in between. And among these numbers, there could be prime numbers. So we should not overlook this thing. If we divide this number by primes p1 through pn, then it cannot divide, right? If we try to divide. But some number in between may divide this n. Do you know what I mean? Do you get it? These numbers p1 through pn cannot divide n. But some number in between, right? Some number in between here may divide n. That means this is not necessarily a prime. Are you confused, or do you have the picture clearly? So in the proof, we assume that these are only prime. These are the only primes, then this is prime. But if we lift the assumption, in other words, if we get rid of the assumption, then what happens? We collect primes like this. Then this is not necessarily prime, because these are not divided by this finite set, but these may be divided by some number in between. So it's not necessarily a prime. So I explained these things last time and this time. If you are still confused, ask me. Then my claim. Between first prime p1, right? This is the first prime p1, second prime, and then nth prime, right? Between nth prime and then 1 plus multiple of n prime numbers, there should be a prime. So this is the claim. Do you get it? There are prime numbers p1 through pn, and then we have a number. It's not necessarily a prime, but we create a number. Then there should be a prime between this and this one. If we don't have any prime in between, then this is the prime by the proof that I showed you. Do you follow me or not? Any questions? So take a look. P1 through Pn are primes, first through nth prime. Then the next prime, say P plus m, P sub m plus 1, should be less than or equal to this prime. That's the claim. Do you get it or not? The proof is exactly the same. Why? Because assume that there are no primes in between. Assume that there are no primes in between. Then this number is not divided by P1, P2, Pn, right? This number cannot be divided by P1, P2, Pn. And then there are no primes in between. Then this is a prime. Do you follow me or not? Exactly the same proof. If you don't understand, ask. It's exactly the same proof. Assume that we order prime numbers. First prime says 2, 3, 5, and so on. Then the next prime, say p sub n plus 1, should be between this pn and 1 plus p1 through pn. Why? If there is no prime in between, then any number, any composite number should be divided by these primes, right? But this is not divided by p1 through pn. That means this itself is a prime. So I will write the theorem or corollary. So where is the theorem or corollary? I think it didn't have any statement there, but it is a statement about page 47, and about first and then second paragraph. That is line, I count the line number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 18th line, right? Line number 18 has this statement. Pn plus 1 should be less than or equal to P1, P2 multiplied all the way up to Pn plus 1. So I describe the proof. Assume that there is no prime in between, then this itself is a prime, right? And that's the end of the story, because Pn plus 1 represents the next prime after Pn. Do you get it? So here we are handling proofs. Very different matter than the calculation or formula. Very different thing. Then with this, we can write a lot of estimation, and people did nice estimation. As you can see, theorem 3.5 says Pnth prime is less than or equal to 2 to the power of n minus 1. So she claims this thing. Then we use the previous fact with induction. So I will briefly show you the proof of this thing. First of all, P1 is first prime 2, right? And then P1 equals 2 is less than or equal to 2 to the power of 2 minus 1. I mean, n is 1, right? N minus 1 minus 1. Because 2 to the power of 0 is 1. And then 2 to the power of 1 is 1, right? 2 to the power of 1 is 2. So 2 is less than or equal to 2. So this is correct. So assume this for k. Then p sub k is less than or equal to 2 to the power of k minus 1. Then the next thing is P maybe easier proof can exist, but I will show this. P is 1, 2 to the power of 1 minus 1. P2 is less than or equal to 2 to the power of 2 minus 1, all the way up to P sub k, 2 to the power of k minus 1, right? Then multiply everything. if we multiply everything, what happens? P1, P2, Pk is less than or equal to 2 to the power of this thing, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of k minus 1. Because we are multiplying these things, we add in the exponent, right? Then what is this sum? 1 added up to this thing is, so 2 to the power of 0 plus 2 to the power of k minus 1 equals 2 to the power of k minus 1. Do you follow me? Oh, excuse me. So I will write it. This is straightforward calculation. 2 to the power of 2 to the power of k minus 1. Why? Because of the induction. Then, by the previous statement that I gave you, p to the power of k plus 1 prime is less than or equal to 1 plus p1, p2, pk, right? By the previous statement that I made, k plus first prime is less than or equal to the product of all the primes plus 1, right? All the previous plus 1. Then, this is less than or equal to 1 plus, because of this fact, 2 to the power of k minus 1. Then this is less than or equal to 2 to the power of k, or 2 to the power of k plus 1 minus 1, right? Then done, right? So we prove this fact for k plus 1, assuming k. So we prove this by using induction. So as you can see, even the case like this is not easy to prove. It's a whole new different ball game, right? Proving something. So I don't want to cover too many proofs today, and I want to describe what kind of things are considered. But if you don't understand some part here, some rigorous part here, then ask me. For instance, I don't know why this part is so, and so on, then you may ask. Then let's continue. There are many claims, and there are some interesting claims. Bertrand made this claim. Between n and 2n, there is a prime. So for n greater than or equal to 2, there exists a prime p between n and 2n. So let's pick some number n, for instance 3 or even 2. Between 2 and 2 times 2, 4. Between 2 and 4, 3. 3 is prime, right? And what is the next number? 3. Then 3 and 6. Between 3 and 6, we have 5. The next number 4. Between 4 and 8, we have 5 or 7. Between 5 and 10, we have 7. Between 6 and 12, 11, or some number. So we have prime. But still, nobody could prove this. So this problem is open. People can understand the statement, right? People can understand this statement, but nobody could prove this thing. It's the open question. So there are thousands of open questions in number theory. So people have specialty. Number theorists themselves have specialties. Some people work on this problem, that problem. This is open. Another problem is this. Assume that you pick even number, which is greater than or equal to 4. Then it is the sum of two prime numbers. For instance, 4, 2 plus 2. 6, 3 plus 3. Right? 8, 3 plus 5. 10, 5 plus 5 or 3 plus 7. 12, 5 plus 7. So, some person find this thing and conjectured, and this is called Goldbach conjecture. He said this happens all the time. And what is it? Still open. So instead of proving it, I'm showing that people failed to prove this. Another thing is this thing. We call these twin primes. For instance, 3 and then 2 numbers later, 5, right? What else? 5 and then 2 numbers later, 7. And then 11 and then 2 numbers later, 13. Because if it is even automatically composite, right? So we should skip 2 numbers. So these are called twin primes. Then what is the question? Are there infinitely many of this sort or not? And this problem is still open. Nobody could prove it or solve this problem. So once we consider prime numbers, there are very many nice open problems. And there are some improvements, but I don't want to be too specific because of the previous proofs. You might be already confused, so I want to introduce what kind of things are there. But roughly these are the questions, open questions, famous open questions. And the next thing is prime of some pattern. For instance, pick 2 numbers. Any 2 numbers are okay. Pick any other than even, just a moment, even, right. Any 2 numbers which are relatively prime. 2 numbers which are relative. Did you hear the definition of relative prime numbers? And the GCD is 1. They are called relative. So please pick 2 relatively prime numbers. 25? Then, what about this kind of thing? 12 multiplied by any n, and then 25 added, or vice versa. 25 multiplied by any n plus 12. So the question is this. We have infinitely many numbers of this pattern. Then among these numbers, how many primes can we get? That's the question. Do you follow me or not? Do you understand the situation, or should I re-describe this thing? So for some people, not all, for some people I will re-describe it. So the first part will be re-described. 25, and then 12 added here, then 37, 12 added here, 49, 12 added here, 61, 12 added here, 12 added here, and so, right? So we have infinitely many numbers of this pattern. The second thing, 12, 25 added here, then 37, right? 25 added, right? And then 87, 112, 137, 162, 187, and so, right? So this is the meaning. So assume that we consider these things called arithmetic progression. Then inside the set, how many prime numbers can you extract? From the first set, how many do you guess? Let's make the problem easier. Infinitely many or finite many? What is your guess? Infinitely many. So in the first set, there are infinitely many prime numbers. In the second set, how many? Infinitely many. And my question is this open or not? This is not open. Somebody figured out and then proved it. Dirichlet proved this thing called Dirichlet theorem about arithmetic progression, and it says if we have two relatively prime numbers, then any possible arithmetic progression, right, using AB has infinitely many primes inside this set, right? Inside this kind of set. So infinitely many prime numbers here and infinitely many prime numbers here. Of course, in this course we don't prove it, but if you are interested, I can show you the proof part. But in any case, it is very remarkable achievement, right? Take a look. Other things look easier but couldn't prove, right? Other things look easier but couldn't prove. This thing looked harder, but he proved. And you will see one example, 4 and 3 case. 4 and 3 case you will see. So we can write the numbers in this pattern. If we divide any number by 4, then the remainder could be 0, 1, 2, 3. If the remainder is 0, then 4 times n automatically composite, right? Automatically composite. If the remainder is 2, then 2 can be extracted. Then 2 times something automatically composite. So there are 2 possible cases, 1 and 3. 1 is harder to prove. So we will prove 3. Do you follow me? So we will prove just one example, but he proved all the possible cases. Amazing achievement, right? So you will appreciate his achievement once you see the proof of just one case. But he proved for any combination of relatively prime numbers. But let's do the proof later, because as I mentioned, I don't want to prove too many things today. Then there are questions, interesting questions. How many consecutive prime numbers in this arithmetic progression? In other words, 4n plus 3, I will write it, and then you may extract n equals 0, then 3, right? N equals 1, 7. N equals 2, then 11, 15, and then 19, and then 23, and then 27, and then 31, 35, 39, right? Take a look. What is prime? This is prime. This is prime. So we got 3 consecutive prime numbers in this progression. And we get 2 consecutive one, and so on. And then we may go this way, right? So people considered this kind of thing. How many can we find? I'm not interested in this kind of direction, but some mathematicians do research on this kind of direction, right? Consecutive prime. Opposite problem is consecutive composite. Give me a number. Give me a number. Give me one number. 28. Can someone pick outrageously bigger number than 28? Wow. Someone can pick bigger number than this outrageously, not just. So I will pick, instead of you letting you pick, I will pick this number. Will this be enough? I can pick, in fact, any number. Then I can find these many consecutive composite numbers. So prime number is tough to really find, right? Consecutive primes are difficult to find, but consecutive composite is easily found. For instance, (24), (25), (26), (27), (28). Take a look. I picked 5 consecutive composite numbers. Take a look. Composite, right? Composite, and so, right? So I can pick this kind of consecutive composite number. So composite direction. So some direction is easy. So consecutive prime direction is tough. Consecutive composite direction is easy. I will show you. So I don't want to write this. So I will call this number, I'll use the old letter alpha, right? Alpha. So I will show you that I have consecutive alpha composite numbers. Alpha plus 1 factorial plus 2. And then alpha plus 1 factorial plus 3. And then all the way in the end, alpha plus 1 factorial plus alpha. Even alpha plus 1 is possible, right? But in any case, take a look. This is divided by 2. This is divided by 2. Some factorial is divided by the previous factor, right? 2. So this is divided by 2. This is divided by 3. This is divided by 4. This is divided by alpha. So all these numbers are composite, right? And consecutive. So it's not very difficult to create consecutive composite numbers. It's tough to create consecutive consecutive primes in arithmetic progression, but it's not very difficult to create consecutive composite numbers. Assume that you are considering this problem in arithmetic progression, then you increase this number using, for instance, 4, right? So 4 alpha plus 1 up to something, right? And then we add these things, then we can find consecutive composite numbers in any arithmetic progression. So it's an application problem that is not very difficult. Do you follow me? So consecutive composite is not difficult to create. Then what else is there? Formula leading to prime. For instance, n squared plus n plus 41. So use integer. N equals 0, prime, right? N equals 1. What is it? 43, prime, right? N equals 2. 47, prime. N equals 3. 12 added here, 53, prime. So there are two considerations. First consideration is doomed very early. Will there be a formula generating all the prime numbers? The answer is no. There is no formula generating all the prime numbers. Meaning, I have a formula, say f function, and f of 1 gives us 2, f of 2 gives us 3, f of 3 gives us the next prime, 5, f of 4 gives us 7. There is no function like this. There is no function like this. We cannot make function like this. So we cannot cover all the primes. The next question is this. So let's relax the condition. F of 1 is 2. F of 2 is also 2. F of 3 is 3. F of 4 is also 3. F of 5 is also 3 or even 2, right? 3 or 2, right? Even 2 is okay, right? So will there be a formula like this? Can you see the difference? This is the exact match. This is not exact, but at least cover all the prime numbers, right? 2 is covered, 3 is covered, and then so on, right? Will there be a function like this? Answer is no. There is no function like this. So we gave up the first question, we gave up the second question. Then the third possible question. F of n is just prime. Can you find this kind of function? Can you find this kind of function? F of n is just prime. It is not necessarily covering all the prime. Do you know what I mean? Do you see the difference between this problem and the previous problem? Previous one should cover all the primes. But this case covers just possible prime. In other words, can you create formula doing this? And there are some debate about some function. Someone used 26 variable function. Someone used 24 variable function and so on. And they claim that lead to a prime, but they have some condition. If these are satisfied, this is prime. So that kind of condition exists. So there is some debate on this thing. And someone proved the existence of the possibility. Existence. So there is a number, real number R, right? Some real number R. And then R to the power of 3 to the power of n. And then I will define this function very soon. Floor function. Floor function is truncating function. Assume that you have 3.14, then you truncate the decimal, the numbers after the decimal point, right? The fraction part, then you will get 3. So we do this thing, then these are all primes. So I will let you know the one who did this thing. He is W.H. Miller. So he proved that there exists a number R satisfying this. In other words, R to the power of 3n with the truncation, right? With the truncation creates primes. So he proved the existence. Then, can you find it? If you find this number R, you will become very famous. Even the number can be called under your name, right? Like Euler number or some number. Once you find this number R, then your name can be attached. For instance, if Smith finds this, then it's called Smith number, right? Smith number, and then may use letter like this, right? S. S number, right? For instance, 107.11221314 and so on. Assume that someone has found this thing, and the person will become very famous. In addition, the number may be called under the founder's name, right? Under the finder's name, right? Under the finder's name. Any questions? So there are very many problems. So there are about at least 50 number theorists and algebraists at the institution that I studied. Some professors studies on this subject, some professors studies on the other subject, and so on. And sometimes their areas are very different. Some people focus on this thing and spend time on this thing. Some people focus on the other thing, and so on. So these are the introduction part. Then what is the thing that we can consider in this section? Importance of prime. So application is the part. Assume that you are, as I mentioned before, numbers are used every day. Even today you used this thing. For instance, did you see it? Did you use it? Because even if you don't want to see it, the broadcasting companies rely on this thing. Photographing technology uses this thing. Your cell phones use this thing. And chips, like CPUs and so on, use this thing. So numbers everywhere. Then how to apply number theory? For instance, assume that some image is there. Instead of sketching everything, I'll just show you the way people do it. So let's consider black and white, not the colored image. Then we can create 8 by 8 image, and then we consider the depth, right? The grayscale, right? Grayscale can be encoded. So like very dark, 0, very bright, 2 to the power of 8, right? If it's 8 bits, then very dark is 0. Very bright is 2 to the power of 8. 2 to the power of 8 is what? 256, right? Then with this scale, we can represent the depths. So for instance, very bright color, then it is 256. Very dark here, then 0, and so, right? We create these kind of numbers, and then we convert these things. Then, what is the relation between these things and primes? Numbers satisfy what? Numbers satisfy the fundamental theorem of arithmetic, right? So assume that you have 18, then 18 equals 2 to the power of 1 multiplied by 3 to the power of 2, right? So we use primes to handle, especially instead of describing everything, one thing. Once you want to send your message, like bomb, so BG, I will not specify the city name, right? BG on February 19th, 5 a.m. So assume that you want to send this message to appropriate person. If you send it and someone may intercept and then catch, but you want to scramble it, right? Then you convert these things to numbers, right? B can be converted, for instance, 2, right? O can be converted like 17. I do not know the exact number, but I'm just showing you, right? So we convert these things. Then it becomes a series of numbers, right? Series of numbers. Then this number is converted by using this prime thing. And then, like, instead of 2, like, instead of 17, and so, right? So this number is received. Then once the other party receives this kind of number, then automatically it should decode, right? It should decode and eventually get the message. Then how can you do it? We use prime numbers, and the big idea is this. We use some number n, and then n is multiplication of two prime numbers, p1 and p2. p1 and p2, two big prime numbers, are multiplied to make n, and then we scramble the message using this n. Then the people knowing this p1 and p2 can easily decode. In other words, your cell devices, right, your cell phones have p1 and p2 information, and then encode and decode very easy. But people who intercepted your message do not know about p1 and p2, then they cannot decode, or it may take very long time, like years, to decode one message. So this kind of technique has patent. I guess now this patent is open, RSA patent. So they even patented two prime numbers. Numbers are patented. So we study this number theory and these proofs and the primes because of the huge application in the world. So let's stop today, and next time I will prove the thing that I couldn't quite finish, and then a few more things.